The last few years, the platform has vastly changed. Automation, monitoring, redundancy are all words that are now part of our platform. But what are the next steps? How can we improve? Building our product begins with software engineers writing code. But how does it transform into a live working website? The platform is what makes it possible. There are many intricate parts to running a website. Before explaining how the platform engineers will improve the process, let's first understand how it currently works. We start from the source code. The first step is to convert it into a machine-readable format called binary. This step is often referred to as building. An application is made of thousands of source files that are built into thousands of binary files. Handling independent files is complicated, therefore binary files are packaged into a single file called an artifact. Once the artifact is packaged, it requires some infrastructure to run. Servers are providing compute, memory, and disk resources. Most of the time, an application also requires a list of dependencies to run. Some examples are Java, Node.js, PHP, and so on. The application and all its required dependencies are then copied to the server, ready to be run. This is referred to as deploying an application. We have more than one application running on more than one server. Resources are constrained and need to be monitored and adjusted continuously depending on usage and new deployments. As we saw, there are 3 different phases to bring an application into production. Phase 1 is building and packaging. Phase 2 is deploying the artifact on the servers. And phase 3 is monitoring and operating applications. Now that we have a better understanding of this process, let's explain it in more depth to determine how to make it more efficient. We have always been packaging, deploying, and operating our applications. However, the process has continuously changed and improved over the years. Back in 2010, all the steps were manual. Software engineers were packaging only 3 artifacts. The packaging was all done on software engineers' computers. In 2011, a 4th application arrived called Expense. In the following years, more and more applications were created. To keep up with the increasing number of applications to package, the platform engineers began to automate the packaging process thanks to an automated build and packaging server called Jenkins. In 2015, all the source codes were now packaged automatically by Jenkins. The platform engineers were now able to only focus on deploying and operating applications. This was only the beginning. The software engineer teams started splitting the applications into smaller applications to simplify the maintenance. The number of artifacts exploded to reach 160 today and counting. Platform engineers are deploying an increasing amount of artifacts. Deploying them all manually was both time-consuming and prone to errors. The number of deployments was growing even faster than the number of applications, as each application is deployed multiple times per year. The logical response was to transition from a manual deployment to an automated deployment. In 2017 and 2018, the platform engineers worked to migrate to Linux and to use Chef to completely automate deployment. Chef is responsible for copying the artifacts into dozens of servers, as well as installing the required dependencies on each server. Each year, the number of deployments continued to grow exponentially. The time saved by automated deployments allowed the platform engineers to focus on operating, improving, and adding new capabilities. As we saw, our platform has reached a state where packaging and deploying is fast and automated. Could we go even faster? Even if our platform is efficient in packaging and deploying, there is still some room for improvement. The monitoring and operating phase is still a manual process. Let's look deeper at the current inefficiencies. We have an expansive set of applications, and most applications require a unique set of infrastructure requirements. First, we have the in-house applications. Those are the applications that are developed by our software engineers, going from Java web application to Java standalone executable application, Node.js applications, and scripts. Those applications rely on third-party software such as databases. We run different databases as each provides different features and capabilities. Applications also rely on different software that provides high availability, redundancy, security, or email service. All deployed applications are monitored using more third-party applications, and internal tools help manage our product internally. Those deployed applications are running on servers that need to be managed and automated. Applications have all different requirements. Some applications need additional storage, others are memory intensive. Critical applications need reliable backup. Applications are also packaged differently. Some applications require dependencies, other applications are installed directly on Linux and just require configuration. For each software being used, there are unique packaging and deployment processes with unique infrastructure requirements, making adoption of new technologies slower. Some of the applications we use are developed in-house, others are third-party. Software engineers are building in-house applications, and platform engineers are responsible for deploying and configuring third-party applications like databases. Software engineers' applications are using third-party applications managed by platform engineers. There is a strong dependency between software engineers and platform engineers when changes are required. There are two teams responsible for a single application. Software engineers are packaging it, and platform engineers are deploying and operating it. Software engineers are building the product on their laptop, running Windows with little to no dependencies, and often running the default configuration for simplicity. Platform engineers are configuring the production environment, running on Linux, having a complete infrastructure to support the applications. Applications are configured with high security in mind to meet our certifications. Containers can help us streamline the deployment. As we saw, the current platform is a diverse environment. New applications or big changes are always slow to deliver because it's impacting more than one team. Moreover, software engineers' environment is really different compared to production environments and can lead to issues during deployment. Before going deeper into what problem containers are solving, let's clarify the confusion between Docker and containers. So what's the difference? Let's take the concept of a car. A car is a four-wheeled road vehicle that is powered by an engine and is able to carry a small number of people. This is called the specification. From this specification, there are dozens of different cars available from different makers. You have fast cars, electric cars, luxury cars, and so on. In software engineering, those are called implementations. Containers are the specifications. A container is a portable, isolated process containing all required dependencies to run. Docker is one of the most famous implementations of containers. Examples of other implementations are CRI-O or Containerd. We saw that our landscape is complicated, diverse, and high maintenance for the platform engineers. Containers are a unified way of packaging various applications. We can use containers to package our in-house Java and web applications. All the infrastructure, monitoring, and internal tools are also good candidates for containerization. Some databases also can be effectively packaged as containers. Migrating to containers reduces the landscape to the minimal core infrastructure. This infrastructure has only one capability of deploying single packaged artifacts, which are our containers. Therefore, deploying new applications is completely transparent for the platform engineers. With containers, software engineers will also have better control over third-party software as they are packaged the same way as in-house applications. As containers are portable, software engineers can run and test on their laptop the exact same containers as the one that will be deployed in production, removing environmental discrepancy. We trim down the complexity of deployment and environment by having a unique artifact to deploy. Operating 100 similar containers is easier than operating 100 different softwares. However, it is still a high maintenance cost without automation. Platform engineers will now run applications in containers. To ensure the applications run correctly, the platform engineers monitor the load of each server. When more resources are required, the platform engineers are adding new servers and are moving some applications to the new available server. To achieve high availability, platform engineers also deploy applications more than once on different servers. But today, platform engineers are operating 160 applications on 95 servers. Organizing and optimizing them is time-consuming. Optimizing resources is important, as having too many empty servers lead to over-maintenance, and on the other hand, overloaded servers lead to poor performance. A single application uses a fixed amount of resources. When too many users access the same application at any given time, it becomes less efficient. To compensate for the performance loss, the application needs to be scaled up. Platform engineers increase the number of times an application is deployed so that an application has more resources available. All the manual operating tasks are time-consuming for the platform engineers. It's also the last part of our three-phase application lifecycle that is not yet automated. How can Kubernetes help in optimizing that last phase? The name Kubernetes comes from the Greek and is pronounced Kubernetes. It translates to captain or governor. Kubernetes is a system for automating deployment, scaling, and managing containerized applications. Kubernetes monitors all servers and automatically ensure that resources are optimized and applications are evenly distributed. Scaling becomes as easy as just adding more servers and connecting them to Kubernetes. It will automatically organize applications and optimize resources to use the new available server based on configuration. Kubernetes is also constantly monitoring each application and can easily detect a failing application. It will automatically deploy a new instance to process requests before a human could intervene. Kubernetes has a lot more technical features that will be explained later. However, it is the last missing piece for a modern platform, as it will bring the application lifecycle from packaging to operating in a completely automated mode.